All right, let's just dive right into this. Welcome to today's Explainer, where we're unpacking Chapter 11 of the book AI-Powered Search, Automating Learning to Rank. Today, we're looking specifically at how modern search engines, they don't just passively hand you results anymore. They're actually actively learning from literally every single click you make to figure out what you actually want.
So it really brings up the ultimate question in search tech, right? How do you teach a search engine to read your mind? I mean, when you type in a few kind of vague keywords, how on earth does the system know exactly what you intended? Framing modern search relevance is really all about teaching artificial intelligence to understand human intent. And to pull that off, we've got to look at the digital footprints, the signals that we all leave behind.
And this right here perfectly sets up our guiding metaphor for the day. Think of a search engine's learning to rank system, which we'll call LTR for short, as a self-driving car. Now, self-driving car is totally useless without a destination, right? In this system, user behavioral signals, like the random stuff we search for, the links we click, the items we actually buy, those act as our GPS coordinates. We absolutely need a reliable way to provide clear, automated directions to our relevance models so they can literally drive users to the correct results.
Now, take a look at the stark contrast between the old way and the new way of generating these GPS directions, which in the industry we call judgments. Back in the day, search engines relied heavily on explicit judgments. This basically meant hiring expensive human raters to sit there and manually grade search results all day. But today, we use implicit judgments. We're talking about free automated user clicks generated by live traffic. Not only is this way cheaper, but it gives us incredibly recent, continuous data that reflects what real users are actually looking for, right at this very moment.
Okay, so how do we actually build this automated system? Well, it's basically a continuous three-step loop. Step 1, we input a new destination. We do this by feeding the LTR system training data based on real user clicks. Step 2, we drive to the destination. The system does this by retraining its ranking model using all that fresh data. And finally, step 3, we ask the classic road trip question, are we there yet? By testing if the new model actually helps users find what they need faster than the old one.
This creates a completely new paradigm for grading relevance. See, when human raters graded search results, they gave absolute binary scores, like a strict 1 for relevant or a 0 for irrelevant, no in between. But by automating this whole thing with click data, we shift over to probabilistic scores. So for example, the movie The Social Network gets a 0.99. What that means is there is a 99% probability a random user is going to find it relevant for that specific query. This percentage-based grading, it's the absolute foundation of automating our training data. But getting to those perfect probabilities isn't nearly as easy as it sounds.
Which brings us to Section 1, the click-through rate trap.
So, the absolute most intuitive way to grade a search result is by using a click-through rate, or CTR, click model. The math here is incredibly straightforward. You literally just take the number of clicks a search result receives and you divide it by the total number of times that result actually appeared on the user's screen. Boom! So, if it's shown 100 times and clicked 10 times, it gets a score of 0.10.
It's a highly logical, kind of naive approach that simply rewards items based on how often they get clicked. Sounds simple enough, right? I mean, what could possibly go wrong with just fully trusting the raw click data?
Well, let's take a look at the results. Here are the ideal judgments generated by our simple CTR model for the search query Transformers Dark of the Moon. Look really closely at the top 3 results here. The model gave its absolute highest score to a Nintendo Wii game and its second highest score to a Nintendo DS game. The actual Blu-ray movie, which is the obvious, most relevant answer, is pushed completely down the list. The raw math has totally failed us here, allowing tangentially related video games to outrank the main movie product.
So the really crucial point here is understanding exactly why CTR fails so spectacularly. It's because of a phenomenon called position bias. Look, human beings are inherently lazy searchers. We have this massive tendency to just click whatever happens to be at the very top of the page, even if the results further down are actually much better matches. CTR doesn't account for human psychology at all. If we train our AI purely on CTR, we are literally just teaching the search engine to blindly reinforce the exact same biased ranking it was already displaying. To teach our self-driving car the correct routes, we're going to need a much smarter algorithm.
That takes us to Section 2, Overcoming Position Bias with SDBN.
To fix our broken data, we first need to introduce a really vital new concept called the examine. An examine is basically a calculated assumption about user behavior.
We assume that if a user scrolled down and clicked on, say, the third search result, they must have consciously looked at or examined results 1, 2, and 3 along the way.
This brilliantly illustrates exactly why examines matter so much. Just look at this typical search session. The user clicks the first result, skips the second one entirely, and clicks the third. The system knows the user examined the second result, that Nintendo Wii game from earlier, but actively chose not to click it. However, the user didn't even scan down far enough to examine the fourth or fifth results. And here's the kicker. If a user never even looks at a result, our algorithm absolutely should not penalize that result's relevance score just because it didn't get a click.
And this brings us to the Simplified Dynamic Bayesian Network, or SDBN for short. Think of it as a much smarter dynamic version of CTR. Instead of dividing clicks by how many times a result was just passively shown, SDBN calculates relevance by dividing the total clicks by the total examines. It brilliantly overcomes position bias by only grading a document when we have actual mathematical confidence that the user looked at it and consciously made a decision about its relevance.
Now, SDBN is a massive upgrade, for sure. But solving position bias actually uncovers our next major hurdle. We get great data for popular searches, yeah. But what happens with rare, long-tail queries? You know, what happens when a user types in a highly specific or maybe badly misspelled query that our search engine almost never sees?
Well, we run headfirst into something called confidence bias. This happens when our training data relies way too heavily on statistically insignificant, completely random events. Imagine a really rare search query that returns an absolutely terrible product, but a single user accidentally clicks on it. Because that document has exactly one examine and one click, the math gives it a perfect 1.0 relevance score. Literally one lucky random click on sparse data can completely ruin our AI's training map. We can't let a few lucky clicks upend our entire ranking model. We need a safety net.
And that leads us to Section 3, the beta prior solution.
Okay, to understand a beta prior, think of a baseball player's batting average. If a rookie comes up to the plate for the very first time ever and gets a hit, their batting average is technically, mathematically, 1,000. But we don't actually believe they're going to hit safely every single time forever, right? We have an initial baseline belief about how a normal player performs. Notice the beta distribution curve here. That curve represents our prior distribution. It's our starting belief about a search result's relevance before we have enough solid click data to prove otherwise.
In practice, we use this beta distribution to set a baseline relevance score. Let's just say it's 0.3. This math acts kind of like a gravitational pull on our data. So if a search result only gets 1 or 2 lucky clicks, the gravity of the beta prior keeps its score anchored right near 0.3. It takes a really significant, consistent amount of user clicks and examines to break that gravity and pull that score all the way up to a 0.9 or drag it down to a 0.1.
Now let's look at the final perfected list. Remember our spectacular failure with the Transformer search earlier? Well, by combining the examine tracking of SDBN with the gravitational safety net of a beta prior, the Blu-ray disc is triumphantly restored to the #1 spot with a dominant score. The video games and the soundtracks, they are appropriately pushed down. We finally actually have a reliable, mathematically sound list of judgments to train our LTR self-driving car.
And we can actually see this success in action with a sparse, rare query for the word dryer. Notice how the beta grades over in the left column are tightly clustered right around our 0.3 baseline? The math smoothly irons out all the chaotic, sparse, noisy data of the real world. It completely prevents any single random accidental click on a hairdryer or a power cord from wildly skewing our AI's understanding of what people searching for laundry appliances actually want.
So, by overcoming position bias and confidence bias, we've successfully automated our training pipeline. It's awesome, but I want to leave you with one final kind of provocative thought here. Our click models are absolutely brilliant at evaluating the results we actually put in front of users. But what about the results buried way back on page 10? If our models only ever learn from what we choose to show users, how do we ever discover what they're missing? That right there is the ultimate conundrum of presentation bias, and a pretty fascinating challenge for another day. Thanks for joining me on this explainer, and keep questioning the data.